Hi, my name is Neely Dupuganti, and I'm going to be presenting the third lab we performed for Physics 2212, which covered magnetic fields. In this lab, it is important to understand that the magnitude of a magnetic field proportionally changes with its separation distance from a particular source. We aim to study the magnetic field produced by a bar magnet by using our smartphones to determine the numerical factor that the separation distance impacts the magnetic field. The system will be isolated to a magnetic field caused purely by the bar magnet, and the results will be compared to the computational model. In this lab, the distance dependence factor was calculated to be -3. The magnetic moment mu was calculated to be 2.965. The experimental net magnetic field at 45 degrees was determined to be 4.821 e -5 teslas, and the computational model yielded 2.031 e -5 teslas. In this presentation, I will cover the fundamental principles, part 1 and 2 of the experiment, the computational model, and I will be answering the additional questions. One of the fundamental principles is that the Earth also exerts a magnetic field. To isolate and study the bar magnet's magnetic field, it must be placed perpendicular to the Earth's field. Further, the Biot-Savart law is crucial to this experiment as it relates a magnetic field to the separation distance and the magnetic moment. The distance dependence equation for the magnetic field is important to calculate the distance dependence factor and the magnetic moment. In part 1 of the experiment, we first had to compensate for magnetic north and locate the magnetometer chip in our phone. Then, the bar magnet was placed at differing distances to produce a determined x component value for the magnetic field, and the distance was recorded. After performing 3 trials for each value, the spreadsheet produced a graph, which could be used to determine the necessary calculations. The spreadsheet of my data is to the left, in which all the yellow boxes include my typed-in data. The graph to the right is very important, as I will use the linear equation produced to calculate n and mu. Using the equation from the graph, the distance dependence factor n is seen to be equal to the slope, which is approximated to -3. This means that the magnetic field is inversely proportional to the cubic distance. Then, the magnetic moment can be calculated by setting the distance-dependent equation to a modified Biot-Savart equation. The value of k can be calculated by raising e to the value of natural log of k from the graph. The magnetic moment can be solved for, which was found to be 2.965 amps times meter squared. In part 2, the bar magnet was placed at a distance where B net equaled 100 microteslas. The y component was recorded, and the phone was moved vertically upwards the same perpendicular distance. At this 45-degree angle, the x, y, and z components of the magnetic field were recorded, and the y component was adjusted to account for Earth. This is just a simple representation showing how this part of the experiment was performed. The phone is at a visible distance d from the bar magnet and is at a 45-degree angle. This is my data from part 2. As can be seen, the average experimental vector for the magnetic field produced at a 45-degree angle at an average distance of 0.285 meters is 3.167 e -6, 2.186 e -5, -4.277 e -5 teslas. The average magnitude is thus 4.821 e -5 teslas. A computational model was constructed to calculate the magnetic field at a 45-degree angle. These are some important sections of the code. First, a function called dipole B was created to calculate the magnetic field due to a dipole at particular locations. 2 on-axis locations and 4 perpendicular locations were created, and arrows represented the magnetic field at these locations. As example, for on-axis location number 1 and for perpendicular location number 1, it can be clearly seen how these 2 different arrows were created. This code was repeated for each arrow created. To calculate the magnetic field at 45 degrees, I input the d-perp value and observation location, then use the dipole B function to calculate the value. In the visual, the 4 cyan arrows represent the electric field at 4 perpendicular distances. The 2 orange arrows represent the electric field at 2 on-axis distances. In the code output, the magnetic field at perpendicular locations are correctly half the magnitude of on-axis magnetic fields, and the magnetic field at 45 degrees was calculated. The experimental and computational values for the magnetic field at 45 degrees can be compared. At a 45-degree angle, the experimental magnetic field was calculated to have a magnitude of 4.821 e -5 teslas. The computational model yielded vector components equaling a magnitude of 2.031 e -5 teslas. Differences in these values can easily be seen. The computational model had nearly 2 times the x component and no z component, unlike the experimental value. To conclude, As the magnetometer moved further away from the magnet, it measured a near zero magnetic field in the x direction and increased as it was moved closer. If I had not oriented the experiment to compensate for magnetic north, the results would have been inaccurate as they would include Earth's magnetic field too. It'd be very difficult to isolate and study the magnetic field produced only by the bar magnet. Lastly, if I were to stick two identical magnets together end to end and run the experiment again, the measurements would be greater since there is a greater magnetic force.